And then later on, I think we were going to talk about like you're going to run us through this visualization that shows COVID-19 in particular.
Yeah.
But then later on, we're going to also look at, you said, the flu and Ebola.
We'll probably flip to those throughout just so that we
Oh,
can
okay.
see, just to show features uh, of the
Okay.
application in different contexts.
So should we get started? I have a lot of questions about the UI, but
Yeah.
maybe you can run through, like maybe you can run through it and then I'll like interject with questions where I have them.
Sure. And thanks so much for, and again, just thanks so much to Shirley for taking the time here to help, to come up with all these questions and taking the time to set the live stream up. Really, really appreciate taking the time.
And thank you for taking the time to like
Yeah.
answer my questions.
All right. So one of the first things that you'll see when you load up Nextstrain is a tree. And as we referenced kind of just a moment ago when we were looking at the Wikipedia page on phylogenetics, this is a family tree of coronaviruses. And one of the things that it's important to understand right off the bat is this is not all cases. What this represents are basically the cases which have been sequenced. So we can think of this as every one of these dots is a person, a swab, and like a nasal swab, and a test. So every node in the tree, and to make it a little bit easier just to think about, since the bottom is also time, we're just going to color by sampling date. And that kind of gives us a smooth color gradient, which matches to the x-axis. We can see that over time, people are sampled. That's the first thing that you can see about this. Mm-hmm. Over time, people are sampled, and then each of these samples is then sequenced. Is sequenced and then becomes data which is fed into these models which create this tree. The other thing to point out right off the bat is that this tree is a kind of best guess. It's a statistical. The tree, every dot are things we know. We know that we sequenced on this date. We know that we sequenced in this place. We know that the sequence we got was this string of ATCG, right? We know the dots represent things we know, and then the tree represents a reconstruction of things that we think. Or a kind of best guess about about how things relate. So, to go over the three areas of Nextstrain, there's a tree which you can see here, and there's a map, and this map is actually showing the tree, and that's kind of interesting. This is the tree, yeah. And if we kind of use the time slider and go all the way back to the beginning, which is going to be kind of a handful of cases in China, then we can also see that we've moved the map back, and this is the root of the tree and all of the branches of the tree spreading out to the dates which are associated with the places people were sampled. So you have we've now scrubbed the time slider and we've reduced the interface to a date range. And then the places on the map are the places that were sequenced, and were available on that date range. And then if we kind of expand the map and we stretch it out, we can see the tree.
Oh, wow.
We can see the tree play out forward. So as we kind of stretch that, we can see more sampling get done. And as that happens, we can then see where that tree relates. So we can kind of go back to the beginning, and then we can kind of go forward.
This is so incredible. I think first, I really appreciate. So when I saw the colors, I didn't think to look into the color by and like look into the drop down and color by anything different. But even just changing this one thing of like changing it to sampling date, like sure, the tree might be like as you expect, but I think that's extremely powerful in the map, because now in the map, you can see. Yeah, like all the cases that happened earlier are kind of the cooler colors.
That's right.
And then the fact that you can also, by the way, this is just like a very technical like detail that I really appreciate, which is that
I think we're going to get pretty technical on this one. I think we need to just go there. So
no, I just mean it's like does not have to do with the virus. It just has to do with the way you visualized it, which is like I appreciate or how this is showing, which is like the links that are drawing and as you like pull through the date range and then the links are slowly drawing through. I love that detail.
I did spend a lot of time with a D3 block in SVG. What that is so the way that that's done is you're occluding a path, so you're drawing part of the path. I think that was one of Bostock's blocks where it's like it shows kind of the path drawing. So you have a path, an SVG path, and then you kind of draw through that space. And then I'm sure it's in a comment somewhere in the code. It's linked to the.
It's actually I think it's the stroke line. It's like there's like an attribute that's like you can
right.
It's like stroke dash array and like
that's exactly right.
Dash.
Yeah. Yep. So you're using stroke dash array to only show part of the SVG path. You draw the path from place to place, and then you use the dash to only show a segment of it. And then if we pull it from the left as well, we can see that we can get partial ones as well. And if we kind of zoom in there, you can see over Uzbekistan and Tajikistan. This represents that this time range neither shows the destination deem. Place. Neither shows the destination nor the nor the originator. And so this is kind of like in the branch, and you can kind of see this up here. If we look at these branches, which are kind of halfway, we're on the way. We're coming from something into something, but we're not there yet.
Mm-hmm. Yeah, and I really appreciate that you did choose to interpolate. Like you could have just like that you tied it to the slider. You could have just like finished the animation and made it automatic, but you chose to interpolate and then map that to the date range itself. So I appreciate that a lot.
There's one more thing that Trevor added since you bring that up. And do you see the thickness of these?
Yeah.
So Trevor then added, if we go back here, you're going to see that each one of those is built up of an individual strand. Mm-hmm. And so that bundle is basically, you're kind of bending along a curve. So you like instead of going straight, it's bent, and then you bend each one a little bit more, and then you end up with as we go forward, you end up with a bundle.
Oh, I appreciate that so much. Oh, I love that detail.
Yeah, we were thinking about line thickness beforehand, and the problem really is that line thickness itself ends up aggregating all the colors, and then you have to show an average color, and it's not as accurate. And so you really want to show each line because each line it does have information, and so we can make that dense. But that is a detail.
Yeah, but I think that's a detail that I'm sure developers would really appreciate as they're like going through the code base. So that actually could potentially lead to a lot of lines. Is this still in SVG or is it in Canvas?
Great question. This is an SVG layer over top of over top.
The performance is really good considering like the number of things on the page.
Yeah, the tree is an SVG as well, and so I think this is something we'll talk throughout. But I mean, maybe it's worth, since we this is meant to onboard developers who've reached out to talk about it, helping to improve. So maybe we'll highlight this in kind of in line here. This is all an the tree is an SVG. Mm-hmm. This is an SVG. It gets to about 3,000, 5,000, 10,000, and then it does face some slowdowns. And so that the performance of that, rewriting the tree in WebGL is a really big lift. I actually think that you might benefit from just moving it to Canvas, which is a much smaller change. And I think personal experience wise, I find that SVG is great for roughly 3,000 elements. If they're not animating, and then once they're animating, then I feel like 1,000 SVG elements is like where but then I think Canvas, I've seen it handle up to like 10,000 animating, and it's still fine.
So I think even just that change from SVG to Canvas is not as big as SVG to WebGL.
Right. So that's one area that, that there is room there for a performance boost. I think probably in both the map and the tree. And that's, we'll put that out to the developer community. If anyone wants to take that monster on, yeah.
We have a question from Hydro Squall.
Sure.
They're asking, when we say that current tree branches are best guesses, does that mean there are uncertainty bounds for the branches or alternative possibilities for the shape of the tree? Oh, what a great question.
It's a great question. So first of all, if we toggle on, well, let me zoom in. So let's go. I want to color by location, and then this is going to be pretty detailed. Let's see. So if we go, all right. So now, and then we're going to filter by admin division, which is or by location. We're going to filter by Washington. Oops, I think that's going to be admin division. There he is, Washington. So this is a case in the U.S. If we, so it's going to be admin division. There we go, because not everything has that. All right, so let's go into this part of the tree. Right, this is all of the local transmissions. Trevor has tweeted a lot about this. This is like the cases that are going on in Washington. They're all in the same part of the tree, and what that means, is that it's likely that it wasn't, lots of different, kind of insertions from China or from Italy or from Korea into Washington State. It was most likely that the community transmission had picked up.
So it's most likely that it probably came over from somewhere else, and then like maybe it's a few people that came over and then it spread, and you said it's a community spread.
Right.
Okay.
Correct.
Okay.
Right, correct. So in this case, let's see. So if we go down to the map is now subset as well, because we've only chosen Washington, right? And so we can kind of trace the path backwards. If we trace the tree backwards, we have a really kind of a smaller subset of the tree here. And so what we can also do now is we can turn on confidence intervals. And this is to answer the question from the stream. This shows us, okay, the tree is, how confident is the model about when the last common ancestor was. So if we know the nodes and we know the number of mutations in the nodes, we should be able to work backwards from there. And we'll get into some of that, what the tree is actually showing and how the tree is constructed. That's going to be, really important details to understanding what Nextstrain is. But the let's see, the node. Let me just go back here. Sorry. Okay. Let me uncheck. Let me clear that from the top.
Okay.
So. If I reset the layout there, if we keep confidence intervals on, we can see that every ancestor in the tree has some date range that is the kind of bounds for the confidence intervals for that date range. And so that answers.
Sorry, can you explain that more? So I think so when you toggle the confidence interval, like there's a kind of a thicker but like lower opacity rectangular block, like a really thin block that comes up. Can you? I'm not quite sure what that means or represents, and how that ties to confidence interval.
Great question. So basically, let's take a look at this red one right here. Can you see this branch that I'm highlighting over?
Yes, and that's and you're talking about the block in the background.
Yes. So this block has to do with this branch, and has to do, and you can see this one up here, how it doesn't go all the way back. This block is centered on this point right here. You can see my mouse, right? Yeah. So this point right here is the best guess, but it could have been the date for the common ancestor for these could have been anywhere from here to here. And we
I
can come
see.
back. It's a great question. I wouldn't have gone to this right away, but just to answer the question.
Yeah,
We
definitely.
yes, it's true. And then the specific answer to the question is there's a time bound. And this will make more sense later on after we've covered some of the more fundamental concepts. There's a time bound around the confidence interval, and then this point of branching represents the best guess. But if you turn on the confidence intervals, it could have been anywhere between February, say 18th, and February 26th. But we think it's on February 25th, et cetera. That's kind of what it's showing.
I see.
So the tree is probabilistic, or the positions of the
The
branches.
The
Yes,
branching is
exactly.
what's probabilistic.
Right.
That's
Yeah.
extremely helpful. Yes.
Yep.
Should we dive into the tree?
Yes, let's do it. So
Okay.
what I'm going to do here is I'm actually going to flip back to Ebola,
Okay.
and just to show a different tree,
Oh, wow.
kind of a different story here. And in this case, we're going to be looking at, let's see, let me just scroll down here. Okay. So if we scroll back, this is the 2015 Ebola outbreak. If we scroll back all the way to the beginning, we can see that we can trace it back to Gekadogu. And what does it mean to trace it back? What does it mean in technical terms? What are we looking at here? So if we go up here and click, we're going to look at what an individual kind of point on the tree is. So let's take a look at that now. So we click on this, and then let's go ahead and go to accession. And what that's going to do is it's going to bring us to NCBI. And if we scroll down, here, we're going to get to the sequence. And so
Sorry. Can you quickly explain accession and NCBI, but only if it's relevant?
Accession and NCBI?
Yes. I'm just trying to.
I see.
Yes, like why you went through the paths you just did just now.
Right. Great question. So accession means kind of where it came from. So so each one of these nodes in the tree, each one of these kind of like the leaves in the tree is a sequence. And so if we click on it, we can then get this. If we click on this, we can say, okay, but bring me to the actual sequence, right? And we can see where the sequence was. We can see this was okay. It's it was taken. The sample was taken in Sierra Leone in the division of Port Loko, and then there's a title as well, right? And authors, etc. And then you have collection dates. So you have some metadata and some metadata about this.
Mm-hmm. Okay. Thank you.
Yep, absolutely. So the sequence is then is the data that was produced by the lab that took that sequence. So in this case, it was probably a blood sample. Could have been blood or urine, I suppose. And I think it varies from virus to virus how the samples are collected. But in this case, you've got let's scroll down to the bottom here. You've got some 18,000 positions. And so this is the entire virus, Ebola virus genome, if that makes sense. And so, so we, each one of these letters could flip, and that's a mutation. So if it flips from a T to a C or a G or an A, or if this G, we would say, the position, 4501 or position, 4530 or whatever has flipped from a C to a T or something like that, right? From one thing to another. Okay, and so what we're the kind of incredible insight here, and this is truly turned into one of the. I think at this point it's got to be one of my favorite pages on the internet. I had never heard of this, and perhaps no reason I would have, but it was such a fascinating concept. I knew nothing about this. Let me show you. So the idea is that of a molecular clock.
Okay.
And so if you head to the Wikipedia page, it gives a pretty great explanation of it. And so a molecular clock. Let's see. Hold on. Here we go. So okay. Right. is this idea that, and it really it changed the entire way that I kind of thought about evolution, and or the kind of the way that I had it in my head, which is that these things flip like at a regular rate, right?
Oh.
And that rate's different for every organism, and that was just like, oh, wild, right? And so that if we know how many hosts it has to be in to flip,
Whoa.
and if we know how many, or on average, right? Again, it's all statistical. Or if we know how much time, then we would know, for instance, if it's got this many mutations, well, it must have been mutating for this long. And that is just totally wild. You take one sample, and then it's this many. If this many letters have flipped, that implies that it's gone through a certain number of hosts. And that's how you can kind of make predictions about how large of a population, for instance, in the case of coronavirus, that there might be, even if you only have a smaller number of samples. And that, to me, was just, that's been one of the most mind-blowing ideas. And I think we should kind of take that back to Nextstrain and then show you how that works.
Yes, that is, yes.
Okay.
Wow, okay, hold on, processing. That is, I didn't know that. That's kind of mind-blowing.
Yeah, and again, I'm an international relations major whose last biology class was at age 14 in high school. I just want to reinforce that for everybody at home. Everything you're hearing here is stuff that I picked up working in the lab with and trying to ask a lot of really basic questions about epidemiology, so that I knew that what I was showing on the screen at various times was what, and then as those conversations emerged, I got like slightly more literate in some of these fundamental concepts, but I'm still very elementary. So basically you've got a mutation, and the mutation in the genome is that one of these flips, and it's kind of helped me understand it too. In apparently, I might have this wrong as well, but I think I heard that like one of the some disorders in human, like sickle cell, is like I think some disorders, sickle cell may or may not be one of them, were just even like one flip. Like if you have one flip, if one of these flips, you've got the disorder, and if and that was kind of also kind of astonishing to learn that the mutation rates happen at with some degree of dependability. I think I had kind of thought beforehand that it was like you have DNA and that's your DNA, and then you have DNA and that's and then I had thought of evolution, I guess, less mechanistically, or mutations as a kind of rarer thing than they actually are, especially in these populations of viruses where they seem to be evolving pretty quickly as they're in the host. That was kind of wild. So that idea kind of blew me away. So let's go back to let's go back now. All right. So if we go back to coronavirus, here, let's see. So now instead of showing time, now we're going to show divergence. And what this means, this is the number of mutations. And that is your big question. And this is why it's so mind-blowing. So we can see that the earlier it is. So if we color by time now, if we make branch length divergent color by time, you can kind of see a trend here that over time you get more mutations. And we can even change the layout to clock, and that's what that means. Over time, you're getting more mutations. So you have 2 mutations from the root, 4 mutations, 6 mutations, 8 mutations, and as you step up, you have here, and that's why this is an integer: 1, 2, 3, 4, 5, 6, 7, 8.
Oh 9. My God!
And then we can actually animate that, and so we can kind of say like, show me, as we move through time, we're actually scrubbing through both time and mutations here. And this is basically showing this is the idea of real-time evolution. We can see that it moves generally upward over time. Over time, we generally have more mutations, right? And if we scroll back, we can see generally we have fewer mutations. And from the root, and as it goes on in the population, and these ATCG flip, that kind of gives you a marker. And so we can this is another big jump here, and then I'll pause. But let's go back to rectangular for a moment, and let's go back down here, and let's click on this, because now if we go over here, let's try to find, this is going to take me a moment because some of these are still private, and the accession is on GSA ID, which I can't click into.
Okay.
So I apologize. I should have thought about this beforehand. I did not.
Okay.
So
I'm still recovering from how mind blown I am now that you've shown me the divergence and clock, and I'm like, oh my God. Does that mean, so I also need to iterate that I was a business and computer science major with like, my last bio class was like 15. And so this is just me trying to put together everything you just said. So is that how because you know the number of diversions, and that's how you have that kind of a confidence interval of where, like, when the branches, when the branches diverted, because you could trace it back to us, like you could make a guess about time and date.
Yes, you can make a guess about time and date. That's right. So let's go. Let's go a little bit more into that. If you go to Ebola and this is all kind of run off the URL. So that's we can talk about the platform side of that as well a little bit. But if we go to clock and we go to time, we can flip back and forth between divergence and time. If we go to time and we go to clock, it'll give us a rate estimate. And now we kind of understand this, right? Substitutions per site per year. And across all of Ebola, if we go to the -3, we've got, we've got something like 0.0015 substitutions per site in the genome per year. And that, if we go back to Rectangle here and grab one of these guys, let me go to, hold on, let me see if I can find let's see. Yeah, this looks like all right. So if we go back to Ebola here and we, just an example, let's take a look here. This is position 1. And then all the way down at the bottom here, we've got like position 18,700 and something, right? All right. If we go back to the interface, now we're going to go to another graph. The last graph, which has the map, is this. Take a look. 18,000. And this is the substitutions on the sites. Oh my gosh. So this, if we click this here, then we can say, aha. So what's happened here, right, is that something's flipped, and it may make a little bit more sense here if we go to nucleotide rather than that. Okay, so it's going to flip from, let's see, if we go to the nucleotide, here we go. This should be, okay, so there you go. So it's we've got an A most places, but then it mutates, and it's a G. And everything after that has the G, which means that you can use that like a kind of marker to say, if I got it, if there's like a few people, right, and one of them has the G, and they all go to a stadium, and someone else gets sick, and you say, okay, you had the one with the mutation as a G, and the other two had the mutation with the A. Let's sequence someone else in the crowd and see whether they had at this particular, at position 347, was it an A or was it a G? And if it was a G, we can say, aha, by sequencing the genome, we can say that we've had some success in tracking it probabilistically. Probabilistically, you got it from this other person. I think it's actually kind of an interesting case here too, because if we zoom in, it looks like it either mutated back or I'm not sure which. Yeah, look at that. Yep. So.
Oh wow.
So this one's I can't explain that. That would be for the scientists to say whether that had they thought that had mutated back or whether they thought that had just I don't know. I don't know why. So let's see. If we go to nucleoside, here we go. So here's a different one.
Okay. I'm going to ask, you just did like a series of actions that were like super smooth and super fast throughout the tool because you're like super in tune with the tool. And I'm trying to figure out if like I should understand what you did as like a general population layperson trying to understand what's going on, or is that more helpful for like the scientists that are using this tool?
That's a great question, and so I think that there's a broader question or idea there, like who is this tool for, and what is the intended audience? And I think, that to my understanding from the lab's intention, there are a number of audiences. Public health officials are not all of them program, right? Some of they're making decisions about population health. They're not necessarily computational biologists, and so going from the insights that we have in a Jupyter notebook, right, in Python, to something that's digestible for people to explore. I think this kind of gets to the motivation of like, why build an explorer? Because every visualization that we're showing here can be generated in Jupyter notebook. There's nothing here that, right, the map, the combinatorics and the, as you said, kind of flying through the high dimensional space, that's the part that the telling stories, and especially the number of combinations of stories that you can tell. If you're a researcher or a public health official and you're just working in Korea, then and let's go back to coronavirus here. Let's see, if we're going to Korea, there we go. So we'll go to South Korea. Then perhaps you're going to be interested just in this. Let's see, color by sampling date. Perhaps you're going to be interested just in this part of the tree and who's transmitting to me and when, right? And how many kind of like insertion events were there, right, in the country, or was just one and then local transmission? Were there multiple passengers from airplanes that from different places that came in? If suddenly tons of the strain in South Korea showed up in some other place in the world, that might be interesting from a kind of a surveillance and a perspective to kind of see who is transmitting to where. Let's see. And I think also it's interesting from the scientist perspective in that if we go back to Ebola, and I'm actually just going to open up Nextstrain here, Ebola, so that I can kind of show you. Let's see, Ebola 2013, 2016. Okay. All right. So in this case, we have a. Let me just. Okay. Yeah. So if we go to author here and we go to Ladner, right, here's where that author, if we zoom out here, here's where that author was sequencing. Ladner is sequencing in Liberia. And here's the tree that he might produce in an academic paper.
I see.
And then if we do Goba et al. Over here, here's the tree that Goba is going to produce maybe in his paper on the kind of, phylogenetics. But that's fine from like maybe a public health research perspective, and they might even share data, but that data might have to be partnership. It's not necessarily open data, right? So encouraging the open sharing of data, getting one big tree. The idea that there's going to be like one tree where all of the open genomes are, that's not, we can't take that for granted. That's part of that's actually really, really new. And so the idea that like, okay, in a public health event, we need to share we should sequence and we should share the genome like right away. Even though it might mean that we get, there's sensitivity about getting scooped on publication. You may have noticed that before I was clicking on these nodes, but they're all GISAID. And if we click on that, then it's just going to bring us to the home page, right? Because these are not necessarily, this requires a login. And so this facilitates sharing of flu data or of other genome data. And to my understanding, though I could be wrong about this as well, this one is more just for scientists so that they can share data with each other, but there's more strict rules about how you use it. Whereas this one, while you may have to cite or may not, I don't know. This one is out in the open, and anybody can grab all of the genomes for the Ebola 2015. Maybe they've already published and they put them up on NCBI. But basically, these are more open. So there are degrees of sharing, in some cases, I mean, I think in some communities in the epidemiological community, I think this is pretty, like Dropbox or sharing genomes around. This is still a work in progress in terms of how do we share lots of data quickly so that we can all see it at the same time. And part of the idea of the platform motivation there is like, if you're a scientist and you upload your data to Nextstrain, you can see it in the context of all of the other data, and you can get insights about your own data too. And again, scientists can do that on their own in Jupyter Notebook locally. That's not something that, Nextstrain's not the only place to do that. That's more of a data sharing issue. But there is some incentive, right, then to say, if we get all of the data in one place, in a place where everyone can, view it and explore it in a tool, that there's a good amount of motivation to have that kind of single place. And so if we scroll back, we can see also from the public health perspective, Goba, and see we can find the common ancestors. So even though we've got two different authors sequencing in two different countries, we can see the places where perhaps there was a transmission event from Sierra Leone to Liberia. And so the sequences in one place instruct maybe the travel routes or surveillance that would be, and then Liberia is potentially transmitting back to Sierra Leone. So this is okay. So I want to show you one thing with this as well, because it's kind of an interesting visualization. I'm going to reset this. So what we can also see here over time, and just kind of before we move back, this map has an animation on it, and we can scrub through the date range. So we have some wait, actually, I'm sorry. I want to slow down for a minute, and I want to kind of go back to the root of this conversation before we move on to that. So I think what we were talking about there was kind of some of the purpose and the audience for this.
Yeah.
Who's the audience? What do they get from it? In what, and if you're looking at the interface, what should you understand as a layperson versus what should the public health official understand, and who's making decisions in this, et cetera. And so transmission tracking is one thing that we can, if we have all of the samples in one place, then transmission tracking is something that we can do using the tool. All right, so let me just reset here. Okay. All right, and I'll zoom out a little bit. Oh my goodness, it's taken me to Mapbox. I'm not sure what I accidentally clicked. I think I clicked the bottom there. Okay,
the improve this map part, yeah.
I think I did click, yeah. All right. So actually, maybe I should pause there for a moment and just catch our breath, because that's a lot. That was like all the way from divergence through some of the more considerations of where the data comes from.
Yeah, I think it was really awesome. I think you've covered all three of the visualizations, and obviously, like, you've covered some in more detail than others. You're right. Like, the divergence one is extremely interesting. So, like, for context, when I reached out to Colin, I sent him a bunch of questions, and then for each visualization, I had a set of questions. And then for the divergence one, I was like, what this? I don't understand. And then Colin was like, this is the most exciting part, which it was. And I actually do want to slow down a little bit and just kind of understand. I'm going to take it back to, because I think the divergence, the clock, I think that was so interesting. And then when you went down to was it called entropy, the very last one that's kind of like a thin bar chart, like the one at the very bottom?
Yes, that's right.
And then so that one, so I think you breezed through this super quickly, and so you're saying that each virus. Oh, actually, before I get into that, I just want to ask a tangential question,
Sure.
which is and make a comment, both tangential, which is as a normal person, my kind of question is when this gets sequenced and and it's put online. The part that's put online is, you said, purely the virus, and so it should not contain any anything about the individual person or anything.
That's a great question. So the data about patients is protected. That's correct. What you have is you have meta-analysis, metadata. Sorry, where the sample was taken, where the sample was taken, where the administrative division and the country and locale, things like that. So U.S., Washington State, and then date. You have things like that. But
then, it wouldn't be I look at the DNA sequence and I'm like, oh, it's this. Again, with my very rudimentary biology.
That's a great question. So if you're sequencing the DNA, if you're taking a swab and you're doing sequencing, can't you put that on 23andMe and what would and aren't you sequencing a person? That's a great question. When you get a sample from someone, so here's something else that completely blew my mind. All right, so do you know what a min ion is?
No.
All right, I didn't either. So this was new to me. Okay, so if you
yes, I do.
I have done
know
that
what that
a lot of times. That is not what I'm talking about. Sequencer, but we'll take that too. All right, so if you go to images here and let's see, this thing is wild. So for field sequencing, we're talking about backpack, like sequencing virus genomes from samples and setting up mobile labs or setting up very small scale laboratories. This is not as expensive as it was. It's about $1,000 or $900 per sequence. So, that's an interesting kind of idea. When you're looking at this, every one of the dots is about $1,000.
What?
So if we go back to like time here to make so they don't overlap. So every one of the dots, so you're 477 genome sampled. The equipment, you can sample a genome for about $1,000 plus like the time of the lab technician and everything else. So every one of these, so there's like $477,000 worth of like this stuff, though that's not necessarily what they used. I don't know if they used a MinION for all these. I just know that like this is cheaper sequencing, and it happened. It's cost of sequencing is coming down, and so that's like another thing that kind of as a metric kind of blew my mind as I walked in one day to the lab and Ali Black was sequencing and helpfully explained where everything was, and it was actually that thing sitting on her desk. And I was like, I'm sorry, come again? Like that's really it's cool. Like you got a wet line, and this is actually, I believe, this is fluid right here. So you're this little like curvy S path right here. To my understanding, that's fluid. So you're putting like you're going through a number of steps in the lab to get the sample and then prepared, and then you I'm going to say the word PCR, and everyone can laugh at me because I don't actually. I know that PCR has probably happened before. They use the pipette to drop it in there. But if you're a biologist following along at home, you know how little I know about that. So the and then it's basically going to snake through here and get sequenced. And then what you're going to get from that is you're going to get a lot of different things, right? You are going to sequence a lot of different, and you're actually going to sequence the virus a whole bunch of times. And so what you're doing is my understanding of this, and I continue to preface that with anything because again I've never done this. My understanding is that roughly what's happening is that you're chopping the genome, you're chopping it into tinier bits. And then you have a reference genome. So we've sequenced Ebola, or you have a reference, and you've sequenced coronavirus. And then you basically match up the little short snippets that might be like 100 base pairs like long, and you align them. And so let's say you have like 10,000 virus genomes in there. And then you say, okay, this maps to that part, that maps to that part, that maps to that part, that maps to that part. And then you kind of do that a whole bunch of times from what you read. And then you get kind of like a consensus sequence, which then is like, you can kind of read across and that's what goes up on NCBI.
The 18,000 that we saw.
Let's just say 100,000. Yes, exactly. So let's say you have 100,000, like total strands counted of the virus that were in the person's sample from a swab or whatever, or from a urine sample or from a blood sample. And then again, I'm making these numbers up. I'm not a biologist, and so and then the idea is that you kind of that yes, that's what this is. You do a sample, you run it through some kind of a sequencing process, which could be even in the lab or in the field, like in pretty near. I think some of the quickest that I saw were like 4 days. They've sampled online, sampled in Nextstrain, and so. The more that the quicker that gets, the cheaper that gets, the more that we can do things like this to see, and that's as real time as it gets right now.
Yeah. So basically, takes the person's DNA and lifts the virus DNA out of it, put it online.
Yes.
That's
right. Exactly.
Sorry, that's an oversimplification, but for
no. That's right. This is the virus genome, not the person's genome.
That's really helpful to know. And for a peace of mind. Right. I also want to say, I really, I see why it gets so political if each test is like $1,000. But that's a tangent that I don't think we want to go down.
To be clear, this is a sequence. It's not necessary to sequence the genome of the virus to determine whether or not someone has it or not.
Got it. Okay. That's really helpful to know also. And the other tangential note that I wanted to briefly mention is like we are talking a lot about like being able to survey like where it came from, where it where the virus transmitted from, where it transmits back, or like where it might transmit to. And I just do want to make like a comment about racism and xenophobia, because
Please.
I think, I just want to make a comment like that. Well, I don't know what to say about it. It's not helpful. I hope that like, what this tool is trying to show with like tracing everything back to maybe like the root. I hope that people don't then take that like what was with such good intention and take it and do something hateful. So I do want to just make that comment really quickly.
Yeah, and I think from a public health perspective, then there's nothing helpful about that, right?
Yeah.
We are all globally. I think if anything, this makes clear how much we're all in this together, and how much one country's response can determine everyone else's. And I think that I'm not in a position to comment or qualified to say, the various responses from various organizations or agencies around the world. But, I will say one of the ones that was most inspiring to me was the Korean response. The universal healthcare, and they had set up. And let me just show that real quick. Let me go to. Let me find. Hold on a second here. That would be okay. So Korea mobile testing coronavirus drive-through. So Korea seems to have set up a drive-through test. Yeah, here it is. Korea seems to have set up a drive-through test where they're testing huge numbers of people a day. Bring your car through, get swabbed. They'll let you know. I don't know exactly whether they let you know there. I'm assuming they don't. I'm assuming they let you know, after the sample gets taken, completely free. We are so far behind in the United States in having that kind of scale and that kind of rapid response to viruses. But we have. I bring that up specifically, in response to what you said, because I think also we have the public health officials have a lot to learn from each other, right?
Yeah, definitely. So yeah, I think that might be a really good place to take a break, and then after we take a break for like maybe 5 minutes,
sure.
Then I want to go back and ask you about the like super speed magic that you did, where you like went to divergence, and then I think you went down to entropy, and then you clicked on like you called it nucleotide, which I don't even remember what that means anymore. And then that showed you where the gene, like where it might have flipped. And so let's pause here and take a break, and then come back, because I feel like there's still so much to cover, right?
Yeah, we could talk for a while about this, but and I'm happy to go on for as long as you have time.